Welcome to Calc Chats 32. Today we're going to be talking about error bounds and remainders, specifically using the Taylor remainder theorem, as well as the alternating series error bound. We've discussed how we can write functions as an infinite series. So given f of x, we use our Taylor polynomial to construct this series that ends up looking like the series from n equals 0 to infinity of the nth derivative of f at a all over n factorial times x minus a to the n. So again, this is just our basic Taylor series that we use to construct these functions and what's really close to these functions. So what ends up being the problem with infinite series is that we don't have a number for infinity. Is what I'm trying to say. And so when we construct these series, we can't go all the way to infinity. We're only human, we're not computers. And so we eventually have to stop at some n. And so we'll say that this is, n can be any number, but it can't be infinity. So n could be 12, n could be 10, and could be 100. But eventually, at some point, we're going to have to stop. And so what we get with these functions is, if we kind of look at this graphically, we have this function, and our Taylor series is getting really, really close to our function. It might be just a little bit off, though. It might be a little bit to the right, to the left, up or down. It's a little bit off. And so when we are composing this series, we add on what we call a remainder. So when we have a finite amount of n terms, we have to add on this remainder, and that kind of accounts for the space between our function and our finite series. So this remainder accounts for that space, and then it kind of tells us basically how far apart the series is from the actual function and how accurate our series is at estimating our function. And thanks to Taylor, we also know that this remainder is equal to the n plus 1th derivative of c over n plus 1 factorial times x minus a to the n plus 1. And c is somewhere in between a and x. So any given a, any given x, is somewhere in between those two values. So this is our remainder, again, when we're dealing with those finite terms of a Taylor series, or Taylor's polynomial. So we have this remainder. And Taylor's theorem with the remainder is that basically kind of what I just said in this slide, that this is the nth plus 1 derivative, and where c is between x and a. And again, we're just kind of, this remainder tells us not exactly, but about how accurate our series is to our actual function. So this is useful because we use it with the remainder bounding theorem. And so I kind of think of this as our worst case scenario. And so what is our worst case scenario? What is kind of the worst possible outcome for how far apart our series and our function are? And so we know that if our remainder, Rn of x, is equal to f n plus 1 c over n plus 1 factorial x minus a to the n plus 1. So when I take the absolute value, remember I'm trying to get the worst case scenario, so I'm really looking for the maximum kind of error. What's the greatest possible error we can find? And so my remainder is without the absolute value bars. Let's erase those for just a second. So when I take the absolute value of this remainder, if I took the absolute value of f to the n plus f, the n plus 1th derivative of c, of f at c over n plus 1 factorial times x minus a to the n plus 1. When I take the absolute value of that, that has to be greater or less than my original n plus 1 derivative. So taking the absolute value just makes this bigger. And so let's say our remainder was 1. Then when I take the absolute value, I'd end up with 1. And so that's great. That's all good and fun. But if let's say this value was -5, when I take the absolute value, that brings up my error a little bit more. And so that's kind of the maximum error that I want to look at. Because again, this is the worst case scenario. So I want to look at what's the maximum possible error I can find. And so we rewrite this as Rn of x. And we say that the absolute value of this has to be less than f to the n plus 1 of, sorry, not f to the n plus 1. We say it's just equal to m times x minus a to the n plus 1 all over n plus 1 factorial, this absolute value. And m, again, kind of is that maximum error bound. So this is, we normally just say m is the maximum value of c on the interval from a to x. So this is just, again, making my error even bigger. This is just trying to get the worst case scenario. What's the biggest error possible? What's the biggest difference between my series and my function, if that makes sense? So m is this maximum value that it takes on to help us find, again, just that worst case scenario. What is the absolute biggest difference that I can have between my series and my function? And this formula that we see kind of up here, I want to make a note. This is what we call the Lagrange error bound. So Lagrange error bound. So we're going to kind of see how this comes into play when we're looking at just basically how accurate our series are. So here's really our first example. So this is asking us to use the Lagrange error bound to estimate the error and using a 4th degree Maclaurin polynomial to approximate cosine of pi over 4. So the first thing we need to do is we need to be able to find the 4th degree Maclaurin polynomial. And so this is cosine of x. This is one of the special ones we have to memorize. And so our 4th degree polynomial is 1 minus x squared over 2 plus x to the 4th over 24. So this is in kind of your Maclaurin table series that we need to know. And so this, since we're not giving anything that it's centered at, we're actually given that it's a Maclaurin polynomial. So the center is just, it's centered at x equals 0. And so kind of going back to our remainder theorem, we were given a polynomial of n degree. We need to find the n plus 1 derivative. And so we need to find the 5th derivative. Since we're given a 4th degree, we got to find the 5th derivative of cosine of x. So we got f of x is cosine of x, so we're going to take f prime, sine of x, f double prime, negative cosine. And we're just going to keep going down the line until we find the fifth derivative. So I'm going to pause there for a second just to write down all of these derivatives But our fifth derivative is negative sine of x. So when I'm looking at this, when I look at the absolute value of sine of x, that can only be at most 1. And so this kind of, again, this maximum value, absolute value of negative sine of x, this absolute value is less than 1, so I'm going to say m is equal to 1. Worst case scenario, we find our greatest value on that interval, and it's 1. So then, you know that Rn of x is less than or equal to m x minus a to the n plus 1 all over n plus 1 factorial. And so I'm just going to plug in everything I know. So I said that m was 1. My x that I'm looking at is I'm looking at pi over 4. My a is where my function is centered at, my series is centered at. And then we're looking at, again, the 5th degree because we were given up to the 4th degree. So that n plus 1, we're going to plug in 4. 4 plus 1 is 5. And then over 5 factorial. So this is about 0.00249. And so the error of the series is about 0.0025. So essentially what this means is that the 4th order Taylor polynomial, or Maclaurin polynomial, this 4th order polynomial, when we use it to approximate cosine of pi over 4, is within 0.0025 of that actual value. So this is a pretty good approximation. There are probably something better, but it's not too bad. And so that's basically what we're using the Lagrange error bound for, is to find out just basically how accurate our estimates are. So the last kind of error bound that we're going to go over is the alternating series error bound. And so when we're given an alternating series, we actually have a different way of calculating the error bound than the normal Lagrange series, or the Lagrange error bound. So that was kind of with positive series. This is with our alternating between positive and negative series. So I need to meet all 3 criteria. And I know in the alternating series, we were looking at, we had -1 to the u of n. We were mostly focused on u of n, but this is kind of focused on the whole thing. And so in my entire series, the terms need to alternate in sign, which is generally pretty obvious. And when I take the absolute value of these terms, they need to decrease, and the terms need to approach 0. So kind of similar to the criteria that we had to meet for the alternating series test. And then if all 3 of these are met, then my truncation error after n terms is less than the absolute value of the n plus 1 term. So basically, this is kind of a Lagrange error. We're taking the n plus 1, but our alternating series error bound tells us that we just take the absolute value of that term and we're good. So this example, suppose we use the first 2 terms of the Maclaurin series for f of x equals 1 plus x. We're trying to approximate f of 0.1. We're going to try to bound the error using the alternating series error bound. And if you remember, ln of 1 plus x, that's one of our special Maclaurin series, and this is an alternating series. And so this is why it's useful to have those memorized, so we can just pull them out, especially with these Lagrange error bounds. And so our polynomial for this is just x minus x squared over 2 for ln of 1 plus x. This is our 2nd degree. So we want to first approximate f of 0.1. So we take 0.1, we plug it in, 0.1 minus 0.1 squared over 2, and this is, that should not be a squiggle, that should be equal to 0.095. So first we calculated that, and then we're trying to find the bound on the error by the alternating series bound. So I need to kind of look back. Do my series terms alternate? Do they decrease? And does the limit approach 0? Or do the terms approach 0? So looking at the Maclaurin series, all of these, well, there's only 2 there, but they are alternating sign, they are going towards 0, and the absolute value is decreasing, so it meets all 3 tests. So basically all I need to do is I need to look at the absolute value of the third term. So I need to look at the absolute value of x cubed over 3 at 0.1. So I'm going to take 0.1 cubed over 3. When I take that absolute value, I find that that is about 3.33 times 10 to the negative 4th. So this number right here, that is my error bound for this alternating series. And if we go through Lagrange error, we're going to find that that is a pretty good estimate for the error. It's a pretty good bound. So I don't have any DIY problems or ABC problems for this because we're still going to be doing some exploration of this in class. So just make sure to come with any questions about the actual theorems, the Lagrange error, the alternating series error. These are really the only 2 that we're going to be focused on. And there are just there's not a lot of problems that we need to know how to do. So just come with an idea of what they are, and then we're going to be working on the problems together in class. So please make sure to like and subscribe to my YouTube channel, and thank you guys for watching.